All right, so far in Chapter 10, we have talked about ordinary cell or air mass thunderstorms. We talked about multi-cell thunderstorms. We've talked about squall lines. We talked about derechos. We talked about mesoscale convective complexes. And now we're really going to graduate to an intense kind of thunderstorm called the supercell thunderstorm, which contains a single violently rotating tilted updraft, which is called the mesocyclone. These are formed in an environment with both speed and directional shear that causes horizontal spin. Now here's what I mean by shear, wind shear. That's when the wind speed increases with height, and that's when the wind direction changes with height. So if I had winds coming out of the south on the surface at 10 miles an hour and I went up 20,000 feet and the winds were from the south at only 20 miles an hour, that's not a lot of shear because first of all the direction didn't change and the speed didn't change too much. But you can get a single violently rotating updraft in a thunderstorm if the winds increase in speed rapidly with height going up above your head, and if the wind direction changes rapidly going above your head. So for instance, if the winds on the surface were from the southeast at 15 miles an hour, but 5 miles above your head the winds were from the west-southwest at 80 miles an hour, then you have both speed shear and you have directional shear. And because of the incredible nature of these supercell thunderstorms, the tops of them can go to above 60,000 feet above the surface of the Earth. Aircraft have encountered hail from supercells in clear air several miles from these supercell storms. There are three kinds of supercell thunderstorms. There are classic supercells, there are high precipitation supercells, and there are low precipitation supercell thunderstorms. You can read the details in your book. But basically, some of them can produce very, very heavy rain. In the late spring and early summer, it's not uncommon on the high plains, say in eastern New Mexico and West Texas, to find low precipitation supercells because the dry air coming down the lee side of the Rockies tends to dry out the lower atmosphere. This is a dramatic picture from your book, Figure 11.22, of a supercell thunderstorm near Sioux City, Iowa on May 28, 2004. All supercell thunderstorms have a vertical, tilted, rotating updraft of air near the back of the storm, which is called a mesocyclone. It can be as much as 3 to 6 miles wide and as tall as the entire height of the thunderstorm. In other words, it could be as maybe 7, 8, 9 miles tall from the surface, from near the surface all the way up to the top of the thunderstorm. Because this is an updraft, this mesocyclone thing, precipitation doesn't fall in it. It produces a part of the cloud which is called a rain-free base. In other words, from the base of the cloud near this mesocyclone, you're not going to get precipitation coming out of it because it's an updraft. A wall cloud may descend from the base of the storm if low-level humid air is drawn into the updraft. And here's a really nice picture, 11.24 from your book, of a wall cloud coming out of a supercell thunderstorm southwest of Norman, Oklahoma. Vertical wind shear plays, as I mentioned in a previous slide, a very important role in supercell development. Again, that means a rapid veering of wind direction with height and a rapid increase in speed of the wind with height. If you have cold, dry air aloft, meaning above your head, over warm, moist air on the surface, meaning down where you are, that produces convective instability. If you have a jet streak or a very strong core of the jet stream aloft right over this convective instability, that increases upper level divergence over the area where surface convergence is developing, and that can often lead to explosive thunderstorm development. The strong vertical wind shear that I mentioned earlier induces counterclockwise rotation in this column of air. Here is a look at a typical upper air sounding for temperature and dew point. Temperature is red, dew point is green there on the left. Figure 11.26. That typically precedes the development of supercell thunderstorms. So you have really warm, moist air on the surface and colder air aloft, which is also very, very dry. And if you look at the stacked graphic on the right, figure 11.25, you can see how the conditions at different levels of the atmosphere change or need to be present in order for supercell thunderstorms to develop. The yellow on the surface part of the map indicates the likely area where supercells will develop. Then in the mid-levels of the atmosphere, say up to 5,000 feet or so above your head, you still have a low-level flow of air coming in from the south. But then you go up a little higher and the winds are coming in from the southwest, and you go up a little higher yet to 18,000 feet, and the winds are coming in more from the west. And then by the time you get to 30,000 feet, that's where you get to the strongest core of the jet stream or the jet streak. So if you have this vertically stacked profile above your head on a particular day, and you live in a place like Texas or Oklahoma, and it's April, May, or June, then look out. There's a probability that you're going to have supercell thunderstorms. This shows the anatomy of a supercell thunderstorm, and that spiral red line going from the base of the cloud up to the overshooting top is the thing called the mesocyclone. That's the single rotating counterclockwise column of air that is the entire height of the cloud and can be anywhere from 3 to 6 miles wide. This shows about 3.5 miles wide, or 5 kilometers. And it's an updraft, so in that rain-free base, you're not going to see precipitation falling out of it. It's a great graphic to study to get a good idea of how these work. As we mentioned in Chapter 9 and also in Chapter 10, dry lines can be significant. A dry line is a sharp boundary between high dew points to the east of it and low dew points to the west of it, often because of very warm, dry air descending on the lee side of the Rocky Mountains in eastern New Mexico and western Texas and northern Mexico in late April, May, and early June. That's when continental tropical air starts to develop over northern Mexico. This is frequently observed in the central and southern plains during the latter part of the spring and the early part of the summer. The hot, dry air can override the warm, moist air, and that produces instability, as seen in Figure 11.27 from your textbook. When strong thunderstorms stall or move very slowly over an area, you can get flooding from thunderstorms. So if a thunderstorm develops and it's particularly intense, and if it's stationary, and if it's not moving very much, and maybe it's over a narrow canyon in the mountains that feeds into a stream or a river, this can cause what we call flash flooding. In other words, a rapid rise of water in an area where water is not particularly common. There are 2 links on this slide. We don't have time in this narration to play them for you, but I want you to play this PowerPoint when you play it and actually get into those links. The first link is a synopsis of the historic and disastrous Big Thompson Canyon flood caused by stalled thunderstorms in Colorado west of Denver on July 31st, 1976. I think it's the greatest loss of life in any weather event in Colorado. 144 people were killed in that. The other link shows a YouTube video from the Kern County Fire Department showing a rapidly developing flash flood in the Lake Isabella area northeast of Bakersfield in the southern Sierra Nevada. Not nearly as big as the Big Thompson, not even by a stretch. No people were killed in that, but you can see how water can rapidly rise in places where it's not even raining because the thunderstorm is somewhere up over a canyon several miles away. So I encourage you to watch those 2 links and get a feel for that. If you look at the distribution of thunderstorms worldwide, on any given day there are about 50,000 thunderstorms that occur. Annually, if you add them all up, it's about 18 million thunderstorms around the world in an entire year on the average. Land masses near the equator and oceans near the equator are areas that are more conducive for development of thunderstorms than anywhere else in the world because you constantly have warm, moist air rising rapidly up where cooler, drier air is aloft. Thunderstorms are much less prevalent in dry climates. Moisture is the key here. In the United States, they are most frequent along the Gulf Coast and also in the state of Florida. Large hail associated with thunderstorms is most frequent over, well, you guessed it, Oklahoma. If you look at a worldwide distribution map of the average number of days annually on which thunderstorms occur throughout the world, you're going to see that the equatorial regions and the persistently moist areas of the world have the greatest likelihood of thunderstorm development, and places that are dry, like the deserts and closer to the North Pole, have the least likelihood of the development of thunderstorms on any given day around the world. This is an interesting map, a figure 11.29, or series of maps. The figure on the left is showing the average number of days annually on which thunderstorms are observed in the United States. Look at where you are in this map, Central California. Fewer than 5 days annually on which a thunderstorm occurs. So, you know, we all get really curious and fascinated here in Central California when a thunderstorm happens. We want to rush out and take a look at it, which can be dangerous because it doesn't happen very often. Figure 11.3, 11.30, I should say, there's a typo there, shows the average number of days annually on which large hail was observed in the United States from thunderstorms between 1980 and 1999. It's a 20-year period there. What is large hail? It's defined as hail that's 3/4 inch diameter or larger, and you can see the bullseye right over Oklahoma. You guessed it. Let's talk a little bit about lightning because it's dangerous. It's a discharge of electricity from mature thunderstorms, and it can be 5 times hotter than the sun's surface, meaning as hot as 30,000 degrees Celsius. You don't want to mess with lightning. The rapid explosive expansion of air as a result of the sound wave caused by lightning is called thunder. Generally, it takes about 5 seconds for thunder to travel 1 mile. So that's the method to use in determining how far away the thunderstorm is from your location. You see the lightning, and then you hear the thunder. And of course, the lightning stroke can travel in a number of directions. It can go cloud to cloud, it can go cloud to air, and the one that can kill you is the cloud to ground one. Those are the most dangerous ones. Here's a bit more about thunder. Now, sometimes the thunder can't be heard, not only because the thunderstorm is too far away from your location as the observer, but the atmosphere tends to bend and stretch sound waves, and those sound waves tend to travel upward away from the observer at the surface. So it's entirely possible that, say, you can see lightning from a thunderstorm 20 miles away, but you may not be able to even hear the thunder from that thunderstorm because of the bending of sound waves. There are many theories about lightning formation. It forms when separate regions of a thundercloud or cumulonimbus cloud contain opposite electrical charges. One theory proposes that clouds become electrified when graupel, meaning ice pellets, and hailstones fall through a region of supercooled liquid droplets and ice crystals in the cloud. Another theory suggests that as precipitation forms in clouds, regions of separate charge exist within tiny droplets and larger precipitation particles. So there are a couple of ways that scientists basically understand how lightning can form. And of course, the discharge that you see visibly is called the lightning stroke. A negative charge at the bottom of the cloud causes a region of the ground below it to become positively charged, mostly on lone protruding objects like a power pole or a tree. And when the insulating properties of air break down, meaning when the electrical potential gradient is high enough, a current flows and lightning occurs. Here's an example of the discharge the charge distribution associated with a mature thunderstorm. When the negative charge near the bottom of the cloud becomes large enough to overcome the air's resistance, the stepped leader rushes toward the Earth. It's very faint, usually invisible to the human eye. You have to take video and slow it down to see it sometimes. Then after the stepped leader, as electrons approach the ground, a region of positive charge moves up into the air through any conducting object, and then you see perhaps a more visible manifestation of lightning. But the most visible is called the return stroke. As electrons approach the ground, well, if we mentioned that, when the downward flow of electrons meets the upward surge of positive charge, then the return stroke occurs. And as we say, it can be cloud to air, or cloud to ground. About 20% of all lightning is cloud to ground lightning, and that's the stuff that can kill you, so you don't want to be near a lone object. There are different forms of lightning depending on the position of the observer relative to the thunderstorm: forked lightning, heat lightning, sheet lightning, ribbon lightning, bead lightning, ball lightning, and then there's one that sailors see sometimes on the mast of a ship called St. Elmo's Fire. Lightning rods are common in structures from the Rockies eastward, homes and commercial buildings, to protect buildings from lightning damage. the other end of the lightning rod is deeply buried in the ground, and that tends to take the electrical conductivity down into the ground. When lightning enters sandy soil, it can create the strange formations called fulguroids, where the heat fuses the sand together. And 11.39 in your book shows how lightning rods work. Here is a cloud-to-ground lightning stroke hitting a 65-foot sycamore tree. You don't want to be there. This is how lightning is dangerous to golfers and to hikers. This was taken, that picture on the right, taken at Sequoia National Park. Lightning detection systems are developed so we can see lightning where it